Is it good? Okay, so where we left off last lecture is we had these three basic components of a computer system. Can everybody hear me, by the way? I don't know if I've actually got the proper mic on. Let me check this. Is that better? Okay, we'll go with that. So we had these three components of a computer system. We talked about the CPU, which is the most complicated one. But let's briefly talk about the other two. So the second component is memory. Okay, so we're going to talk more about memory later, but basically it stores variables. So your program's data. That means simple variables like integers, but also like any data structures you might have, like linked lists or arrays, etc. So those are all technically variables, but let's just write it out. They could be data structures. Don't have to be simple. Anything else go in memory? Okay, so data, you kind of knew that. How else does your program work in C or anything? What else are we going to put in memory? What do you think? Yeah, the instructions. That's where the program itself is going to go. Okay, so that happens when you write a program in C. It gets turned into assembly and then gets put in memory. But it's going to be more kind of in your face when you're writing assembly, right? Like, because you're writing the stuff that goes directly into memory. Okay, so stores the instructions, which are the program being executed. Okay, and then I/O we already talked about. It's diverse, communicates with the outside world. Okay, so on one side it talks to the system bus so that the CPU can control it, send it commands, send it data, etc. And on the other side, it does all sorts of things. Might connect to, the screen, a microphone, an airbag sensor, an accelerometer, a gyroscope, all sorts of stuff, right? A mouse, LEDs, tons of things. You can even connect things that are not I/O. You can connect, so I talked about machine learning. You can connect essentially accelerators, things that the CPU talks to that are hardware blocks that just do some computation, and then the CPU can ask for the result. So in a sense, that's not really talking to the outside world. We're not going to really do that in this course, but basically the same way, you're going to later on in the course see exactly how we hook these I/O devices up to this system bus and let the CPU talk to them. You could hook up hardware accelerators, so blocks of logic that do special purpose communication in exactly this computations in exactly the same way. Okay, so lots of different stuff, right? And I think, because I'm doing two sections of this course, I can't remember what I said to what group. I think we went through a bunch of possible I/O things in the last lecture. Okay, so I won't go through them again. But as I say, kind of even more diverse than that. Could even be accelerators. Okay, so that's it for kind of the overview of, like a very high-level overview of how a computer system works. We're going to, gradually dive into these components further, but that's enough of an overview that we can get going, and now we'll start talking about how we program this system. As we go through the course, we're going to dive into each one of these things and kind of see how do you actually build that. Any questions before I go on? Okay, so now we're going to start looking at how we program this. We're going to program an assembly language. Okay, so assembly language is like the natural, like the actual language of a processor. So a CPU, it's the CPU that runs this assembly language. So the CPU executes instructions, which is your program, to basically control the system. Okay, and it doesn't execute C, it doesn't execute C++, Okay, so it's not C, it's not C++, it's definitely not Python, right? That's even further away from the hardware. JavaScript, all that kind of stuff. It speaks, it's running its native language, assembly language. Okay, and I think I mentioned this to you guys last lecture, but there are a few different variants of assembly language, what are called instruction set architectures. And the variant that we are learning is the RISC-V one, which is a popular one. So it's a good one to learn. All assembly languages look a little different, but a lot alike, right? So once you learn one of them, you can learn another one quite without too much effort. And the other reason we're learning assembly language is not just so you know how to program in this, it's basically, it's what teaches you how a computer really works. You have to understand this in order to really see what's going on. Okay, so let's, to understand assembly language though, it's best to do it by example. So let's take a C program, okay? So here's a C program. It's going to be a really easy C program. Okay, so we're going to take int A, B, sum, and difference, or diff. Okay, how many bits are each of these? So when we're writing things in assembly language, we actually think about how many bits things are and where to put them. So how many bits are each of these things? What do you think? Think back to 244 and 105. You should know how many bits that'll be. How many bits in an integer? Yeah. Yeah, 32 bits. Okay, so okay, we're going to do a very simple computation. We're going to go A equals 2, B equals 9, sum is equal to A plus B, and diff is equal to A minus B. Okay, so writing this in C, there's not a lot of honor to this, okay? But we're going to write it directly in assembler. So when you write this program, you always ran G++ in order to turn it into an executable program that you could actually run. Okay, so normally, like you write C, and the compiler, and a very popular compiler for C and C++ is G++. That's what you used in your labs. Okay, so that compiler does a bunch of work to basically convert this, like create an assembly language program that will actually implement this. Okay, so that is the heart of the compilation process. Okay, so G++ translates this to assembly language. Okay, and usually in assembly languages, we end the file in .s, right? Just like you end files in .c to indicate they're C, you usually end them in .s for assembly. In 244 or 105, did they ever actually show you the assembly output? Probably didn't. Okay, so if you want to see it, you type, G++ will show you the assembly output if you want. You can type G++ -s. And then let's say this was called example.c. Type that, and you'll get a .s file. I think it'll be called example.s, and you can actually go look at it. And you can see, like, okay, what is this actually in assembly? So when you run G++, it normally does two things. The first thing is it takes this example.c, okay, and it does most of what's called compilation. So let's just call that compile. And it makes it into an example.s, which is assembly, okay? And then it actually automatically invokes an assembler, which turns that into machine code, so like a .exe. Okay, so you're going to see in a minute that assembly language looks like a bunch of what are called mnemonics, like short human-readable instructions. And the assembler takes those, which a person can read, and maps them in a very direct way. Most of them just directly map. Like you have a mnemonic, it turns into a certain pattern of bits. So it converts it into a bunch of bits that can actually go into memory and run. So this step actually is the more complicated one. Going from .c to .s is pretty complicated. Going from .s to the actual bits, you could actually do at the end of this course or halfway through this course. It would just be really boring, right? You'd have a big lookup, you'd have a big table of when I see this assembly language instruction, I write down these bits. That's basically what the assembler is doing. So when you do G++-S, you basically tell the compiler, don't do this step. I want you to stop. I want to look at that. So that's always been happening. You just haven't seen it. OK, so what I'm going to do now is we're going to be the compiler. We're going to take that example.c, and we're going to write the assembly language directly to make that happen. OK, so I'm going to put the C line of code. And let's take first line. So declarative variables, int a, b, sum, and difference. OK, and we're going to write down what assembly instruction would do the same thing. And then I'll write down, what does it mean? So what was the function that performed? OK, I have to decide where I want these variables to be. So I could put them in memory, but I want to write a really simple assembly language program. And remember that when we talked about the CPU, it can only add numbers and subtract numbers, like basically do interesting things with numbers if they're in its registers. OK, so if I put them in memory, I'm going to have to bring them into the registers before I can do anything. I could do that, but I don't want to do that yet because I want to keep my assembly language program simple. So I'm going to assume that these are in memory. I should have written that down, actually. Let's see. So we're going to make some assumptions here. And this is part of what a compiler does. A compiler decides where to put all the variables. So we're going to make a choice that is nice and convenient. We're going to put them all in registers. OK, so we're going to assume A is in so variable A. So we're going to put it in T0. So remember, the registers all have two names. They have the X names, and then they have these nicknames. T actually stands for temporary. There's nothing special about them. This is just the same. This is like, I think T0 is like X5 or something. For now, it doesn't really matter. We can use any register we want. But as I said last lecture, when you start writing more complicated programs, other subroutines you call basically will work better if you've used registers in a way that is compatible with them. So these temporary registers are like anything goes. Do whatever you want with them. So I'm going to say I'll use T0. So we're going to put A in T0. I'm going to put B is in T1. And I'm going to put sum in T2. And diff in T3. OK? And it's just, yeah, this is a convenient choice. Saves me having to go do some work with memory, especially because you wouldn't understand those instructions yet. We'll get to those in a lecture or two. What assembly instructions do I need then to make this happen? So in C, you declare your variables. What do I do in assembly language? Should I do anything? Do I need any instructions? What do you think? Yeah, so I'm going to do that next. Where'd my C program go? Yeah, there. So the next line I'm going to write is A equals 2. OK? But that's not yet. I'm just going to do this line by line. So for that one line, I don't actually have to do anything. OK? Because I just said the variables are in registers. I'm going to use them in registers. I don't have to do anything. The registers are just there. They're built into the CPU. So the fact that I say I'm going to put these in the registers, I just remember that. Right? I made a note to myself over there. I'm done. I don't write anything in my assembly language program. Okay, so there's no assembly language program or instruction for that. So we're basically placing the variables in registers. Okay, so A equals 2. So I don't think there's any way you could guess this because you don't know RISC-V assembly language. But the very first RISC-V assembly language instruction that we're going to use is called LI, which means move immediate. Okay, the L makes you think load immediate, so you can also think of that, but they probably should have called this move immediate. And then, so what this means is it means move some data between registers, okay? And in RISC-V, you always give the name of the instruction first, okay? So I said I wanted to do a load immediate, or a better name would be move immediate. You give the destination register. Most instructions, the destination register comes next. So I said that I want A to be in T0. So the destination is T0. I write that next. Okay, and then I put a comma. What do I want to put in there? This particular instruction takes 2 operands, a destination register, and this I stands for immediate, which means constant in assembler language. So it basically means I want to load a constant. What do you think I should write here? Yeah, 2. I got to tell it the constant. There's no way I could know otherwise. Okay, and that's it. Okay, so this is T0 becomes 2, and the mnemonic, that short name, is supposed to make you think of move immediate. Okay, and again, in assembler language, immediate means a constant. Okay, next thing, B equals 9. Okay, so now, given this template, you should be able to get this. Somebody should be able to tell me what to write. What should I write? Yeah. Right. Okay, so I'm going to do another one of these move immediates, but this time I want to put the data into T1 because that's where I said B is. So destination is T1, and I want to put a 9 there. Okay, so T1 becomes 9. Let's see. So next thing, sum equals A plus B. Okay, so another mnemonic that we have is add. Okay, so remember we have that ALU, so it can do a bunch of things for us. So one of the things it can do is add. So the mnemonic add. So I told you that most RISC-V instructions, the destination comes first. Okay, so what's the destination of this add? Where am I trying to put it? Yeah, what do you think? Can you say it loudly? Yeah, so it's T2 because that's where I said sum is. Okay, so T2. So when you're writing assembly language programs, you often have like this little cheat sheet beside you, or you have really well, even better, really well commented code to say like what variable is where, right? Because you kind of have to keep track of it, what you put in various registers. So, and then I give the 2 things that I'm adding. Okay, so the 2 inputs to this instruction, which are A and B. Well, I put A here and I put B there. So T0 and T1. So that's going to add those 2 things. Okay, so it's adding T0 and T1, but because I know I put A in T0 and B in T1, that's adding A and B. Okay, and then this last line here is diff is equal to A minus B. Okay, so there's the handy instruction, sub, right, for subtract. The destination comes first. I said that we were going to put the difference in T3, so this should be T3. And then there's the 2 numbers I'm going to subtract. So I want A minus B. Should I put A first or second? I'm not really sure. I could go on the web and I could look it up. I'm just going to guess T1 first and T0 second. And T1 is, I have to kind of remember what are all these variables. Okay, so this was A, this was B, this was C, and it was the sum of A and B. This, or that's not C, sorry, that's sum. And this is my diff. which I basically said I put B and A. Okay, and I'm hoping that that is diff equals B minus A. But I was kind of lazy. I didn't actually look up which of these is the first operand and which of these is, like, which one is subtracted and which one is not subtracted in this instruction. So for add, the order is not going to matter, right? But for subtract, the order is going to matter. And I didn't bother looking up which one is which. So this is T3 becomes T0 minus T1, maybe. Or maybe it is T1 minus T0. So I'm assuming that it's that, in which case I'm going to get A minus B. But I was lazy, didn't look it up. Maybe I got that instead. Is everybody with me? Yeah. Oh, I forgot to bring a chocolate bar. Okay, you got me. So thank you for finding that. I owe you a chocolate bar next lecture. So I was frazzled for time, forgot to put it in my bag. Okay, I have to be extra careful for the remainder of the lecture now. So, okay, everybody happy with our program? There's one more thing we have to do in an assembly language program that is a bit odd. So all of these instructions are going to get put in memory. I'm going to demonstrate this in the CPU emulator in a minute. And the processor is basically going to start here and just go through them one after the other. Okay, it's going to grab this instruction, look at what it says, do what it says, go to the next instruction, etc. After it finishes this instruction, it's not going to stop. Okay, the processor is going to go on to the next memory location, and I didn't actually put any instructions there. I have no idea what's there. It's going to read them, and it's going to interpret as an instruction, and it's going to do something that is probably crazy, right? And if that one doesn't go crazy, the one after that's going to go crazy. Like, there's no way that this is going to do something useful. So I have to stop it from doing that. When you write a C program, the compiler puts this in for you. Okay, there's code there that stops your program, and it's put in for you automatically. In assembly, we have to just put it in ourselves. So, because we're also running what's called bare metal. Bare metal means we're running right on the CPU with no operating system. An operating system is like another program that can kind of start and stop your programs. We're not doing that in low-cost systems like those greeting cards I talked about and some other systems like your brake system, etc. Often those are run with no operating system because it's going to just be doing one thing. That's why we're using the Neos 5 system because it makes it easier to get to the hardware. You learn more about how to control hardware. And this is done in systems where one person's using them, want to keep it cheap. Okay, so all of that is a long thing saying nothing is going to stop your program if you don't stop it. Okay? So the way we're going to stop it, this is the standard technique, is this line. And I'll explain what it's doing. Okay, so I loop, J, I loop. Okay, so this is just a couple new things. So this I loop is what's called a label. Anything that has a colon after it in assembly language is a label. So it's not an instruction. A label basically is a way for you to refer to the address at which some instruction is placed. Okay? So this instruction is going to get placed somewhere in memory. Actually, if I put this at location 0, instructions in RISC-V are 4 bytes long. This will be at memory location 0. This at 4, 8, 12. This will actually be at 16. Okay? So I could actually say J 0x 1 0, right, which is 16, or I could just write 16, okay? And that would work. But it would only, so I could not use this I loop. I could actually write an address. But that would be a pain because, well, actually, maybe I should explain this a little bit first. So this is a label. I'm going to come back to that in a minute. Let me explain what this is doing. This is called an unconditional jump, okay? So it's a jump statement. And what a jump statement does is instead of going to the next instruction, that's what we did on each of these. The processor finishes this instruction, goes to the next one, goes to the next one, goes to the next one. Next one just means next location in memory. So it knows it's 4 bytes down. When you hit it says don't go to the next instruction because I don't know what's here, right? Some random garbage in memory. You should go or jump to this memory address, okay? So this memory address, as I said, I actually know is address 16. Okay, so this is address 16. This is address 0. This is 4. This is 8. This is 12. This is 16. So I could have written J16. It would work. But that's going to be very inconvenient because I had to actually start counting instructions in order to figure out like what address is this. And if I went back here and I decided I need to add one more instruction, everything shifts down by 1. I have to remember to change this from 16 to 20. So that's going to be a real pain. So to make things easier, assemblers allow you to have what are called labels. So anything that ends in a colon, some name, ends in a colon, that is a label that says what is the address of whatever I put this label on. Okay, in this case, I put the label on an instruction. It says what is the address of that instruction, and I can use it in my program, okay, as a symbol. So this is a symbol that means 16 with my current program, but if I put some more instructions here and this whole thing shifted down, this symbol would mean some other number. So it makes life a bit easier for me. So everybody, okay, so basically, so this is a jump to statement labeled I loop. Okay, and that is an infinite loop. Like this will never end, right? I'm at I loop, I execute this instruction, it says execute it, go back and get the instruction at this same address and execute it again. So the processor's just going to sit there, forever executing this one instruction until I reset it. Okay, so an infinite loop to stop me from going any further and getting garbage instructions. Everybody, any questions on this? Yeah?
Why did you name
It's random. Could have called it Fred. Okay? Could have called it Vaughn. Seemed a little egotistical, right? There's nothing magic about it. A label could be anything else. It's the same as why did I call that variable A or something. Random. Yeah?
Is any assembly language instruction always 4 bytes?
Yes. In RISC-V, every assembly language instruction is 4 bytes. So there are some other processors where that's not true. Like this is part of the design of what's called the instruction set. But it's pretty common that in a lot of languages or a lot of processor architectures, all the instructions are 4 bytes, but not all. In RISC-V, they're all 4 bytes. Any other questions? Okay, so when we're done this is our map of registers, right? We've got T1, T0, T1, T3, which is A, B, sum, and diff, and they'll have the right values in them. Okay, so 2, 9, 11, right? So we should have 11, and our diff should be 2 minus 9 should be negative 7. Okay. So if we've done this properly, that's what we should get at the end. Everybody agree? Okay, so you're with me? Good. Let's send this to the projector and see if the projector's working for me. This is looking promising. Okay, so this program is called Emulator. People started reading the Lab 1 prep. Okay, so you've already seen Emulator. Emulator is going to be your friend in this course. It's what's called an emulator. And how visible is this to the back, actually? Is this pretty visible or not so visible? So? I don't know. I'll play with it after and see if I can make the font bigger. I actually don't know if there's a setting to change the font, but I'll mess around with that later. Okay, so this is an emulator for the Neos 5 system that we're using. So a processor, just goes through instructions doing what they tell it to do. So you can actually write an emulator that is a software program that basically does the same thing, right? It goes through, it reads those instructions, and it'll do exactly what a Neos 5 processor would do. It'll do it more slowly, okay, because the Neos 5 processor is doing it in hardware, and this one is not, right? It has to interpret it with a bunch of software. But it's quite a good emulator. Like this emulator is quite faithful to the hardware. Nothing's ever quite perfect, especially when you get over to the I/O devices. You know, if you're trying to model exactly how a speaker works and stuff, you can start getting some things that are not exactly the same. It's quite good. So you should use this to do your labs, like all your lab preps, test your lab programs, get lots of work done before you go into the actual lab, because you can do it at home. And this is actually written by a former TA in the course, Henry Wong, who now, as I said, designs RISC-V processors now. Okay, so let me write our program here. So the first thing you get in the CPUlator, I mean, it's really easy to bring up, right? It's basically you have a browser, and you type this address in, which is in the documentation for Lab 1, and that's it. CPUlator's up. The first big window you'll see is this editor window, which basically lets you write assembly code. CPUlator has started off with a little bit of code, okay? And this is like boilerplate. It's going to put at the top of every one of your programs. For a really simple program like I'm about to write, I could actually delete it and it will still work. But I recommend you don't do that because we'll get more complicated ones later where it would cause you problems. Let me just quickly explain what it's doing. Anything that starts with a dot is what's called an assembler directive. So it doesn't actually generate instructions. It's a directive, something that controls the assembly process. So this particular one, .global, says the label, okay, so start is a label. Anything with a colon after is a label. So start is actually an address. So this is basically says the label start, which is the address at which my program is going to start. I want to make it global. What that means is if I actually had multiple files, I want you to tell all the files about this label. Okay, so if you make bigger programs, this would be important so that everybody agrees on where does the program start. For a small program we're going to do, it's going to start at 0, doesn't matter. Okay. Anyway, delete that, but that's all it's doing. Now I'm going to start typing in the assembly language program. Okay, so the first thing we said we'd do is load immediate T0, comma 2. The next line, okay, that was getting our A, and actually I should comment this. Okay, so we really want to comment it, so that will be a comment. So this is A becomes 2. I want to do a load immediate of T1 and 9. Okay, so that is B becomes 9. Whoops. I want to do an add. Okay, so T2, T1, T0. So T2 is the destination. T1 and T0 are the inputs. So this is sum becomes A plus B. And diff, whoops, I'm writing my comment first. Okay, so then I want to subtract. T3 is the output. T1 and T0 are the inputs. And that is diff becomes A minus B. Okay, and then I've got to write my infinite loop to stop from going on. Okay, so how do you like my program? It looks good? Okay, so I'm going to screw something up actually. I'll screw something up here on purpose. So I put an extra comma in. And I'm going to hit this compile and load button, and that's going to assemble my program. So when it says compile here, assembling is part of the compilation process. It's just like kind of a more direct part. So I compile and load, and there's a red message down here. Okay, it says compiling. It says compile failed. Okay, so what do I do? What will you do when, okay, you're definitely going to get this. There's no possible way you're going to write your assembly language with no errors. Okay, so you will hit this. What will you do? Okay, I know what to do. I should bring up a browser window and get into Piazza right now, right? So, and I should basically say to some TA, my program doesn't work. I want to give him or her a hint. So I'll say for lab 1, what should I do? No, don't do that. Okay, what do? You read the message, which sounds obvious, but people sometimes don't. And actually, if I read this message, you go, okay, well, this is the command it used to do the assembly. Don't worry about that. It's like given a temporary name to it's kind of created a name for the .s file that it's saved. So there are a few lines here you go, I don't quite know what that means. That's fine. This is the key one. Line 7, we have illegal operands. So it doesn't tell me really what's wrong, but it did tell me line 7. And assembly lines are not very complicated. So I look at this carefully and I see I shouldn't have put a comma there. Okay, so I'm going to save my program and I'm going to compile it again. Okay, so I compile and load, and now it says compile succeeded. So that's good. And you see that actually, let me make this message small again. I've got these little tabs here. I was in the editor tab. It actually switched me over to what it calls the disassembly tab. And the disassembly tab is showing me like what is in memory. It's taken my program, it's turned all of those assembly language, human readable mnemonics, and turned them into machine code. Okay? So it's actually showing me what it's put in memory. So here's the address 0, very first memory location, and opcode is what is the 32-bit value that it figured out as the first instruction of my program. Okay, now that 32-bit value is kind of hard for me to read, right? So it also does what's called disassembling it. So it'll show me in a human readable form what does that mean. Okay, so it says it's load immediate T0, 2. That makes sense. Okay, that's what I actually wrote. And an interesting thing here is you'll see that it's actually showing me the same line twice. I see there's a grayed out load immediate with my comment, and then there's another load immediate 02, which is not grayed out. What CPUlator is doing is anytime what it gets by disassembling an instruction, which is it's just undoing what it did before, right? It took your instructions, turned them into machine code, is now looking at the machine code and showing you what instruction that is. If what it gets is not exactly what you wrote, it'll also show you what you wrote, grayed out. And this is not exactly the same because I had a comment. So it's just trying to be helpful, right? The reason it's showing me this twice is I had a little bit of extra information. If I go down, if I don't like that, if I go down here, it says show source code, I can say none, okay? And now it's shorter. Okay, this is actually only showing me exactly like one line of human readable assembly language for every machine instruction that exists in memory. And if you look at this carefully, you'll see this is exactly what I wrote, but doesn't have the comments. Okay, so I actually kind of like seeing the comments. So I'm going to go back, I'm going to turn the back on. Okay, and now I basically just get lines repeated. I see my comment, one with my comment first, then I see the disassembled one. Does that make sense? So disassembly just means I took it out of memory. And this is like a good way for a debugger to work because it's like guaranteed this is an instruction because I just took it from memory and showed it to you. Okay, so what you want to do, actually when you're debugging anything, you want to have a hypothesis of what's going to happen next and then test it. And you want to do it very systematically. And that's really, it's extra true with assembly language because it's so easy to make mistakes in this. Like if I just get the register number wrong or something, my program is broken. So it's really easy to write a broken program. So you should assume in this course and in general that things are broken until you prove otherwise. So what I'm going to do is I'm not even going to run this yet. I'm going to step through it. Okay, so I go up to the step button and I'm going to do what's called single stepping it. So actually first I'm going to change this back to hexadecimal. And let me show you what this is. Okay, let me get rid of these settings. Okay, so these are the registers. So that's what's being displayed over here. Remember I told you the program counter is really important? Program counter is the address of the next instruction that the processor will execute. So it starts at 0. Okay? And if I look at address 0, I can see there's an instruction there. It's got this encoding, like that's the 32 bits. And the disassembly tells me what it is. It's this load immediate of the number 2. If I press step into and step over are going to behave the same when you don't have subroutines. So I pick one of these step commands, and T0 changed to 2. And you can see it's helpfully highlighted in red. And also the program counter changed to 4. That's telling me the next instruction that gets executed is going to be at address 4. And that's the one that's highlighted in yellow. Okay, so that one hasn't been executed yet. It will be executed next. Okay, so I said you should have a hypothesis of what happens. So when I hit step again, what should happen? You look at the highlighted instruction. That's the one we're going to do next. What's it going to do? This is not hard. So if you go, oh, that's pretty easy, that's fine. Yeah, what do you think?
Use
Right, so T1 should become 9. So let's click on it. Let's see if that happens. Okay, clicked a couple times, but yeah, T1 did become 9, and I actually clicked again by accident. So I went through this line too. So T2 is adding T1 and T0, and it became B. So what is B? What is hexadecimal B? Is that the right answer? So I'm adding 2 and 9. That's what I'm supposed to be doing. Is B 11? Yeah, so B is 11. So this is correct. If you're not that, you're going, this is a pain. I don't want to see this in hexadecimal. Let's go through the next instruction. So I'm going to step over this one. This is my subtraction. I'm trying to do diff equals A minus B. What should I get? A was 2, B was 9. I know you guys know this one. So I should get negative 7. Okay, so I'm going to step over it. And let's see. I got to go look for T3. T3 is way down here. Okay, and it changed to 7. Is that right? What do you think? It's supposed to be negative 7. Okay, so it's wrong. Why is this? What did I do wrong? So it doesn't match my expectation. I gotta fix something. Yeah, what do you think I did? Yeah, so I put these in the wrong order, right? So I have a hypothesis of what's happening. I'm going to go back. I think I put these in the wrong order, so I can go back. I can just edit them right now. So let's put this is T0. Whoops. And this one is T1. And to be honest, it's kind of a more logical order. If I'm doing A minus B, then writing A first and B second seems a little more intuitive. So, okay, I have to recompile. So I compile and load. And it sounds like I might have screwed something up. Let me see if I made a mistake here. Oh, no, the compile did succeed. Okay, so that's good. Okay, so I'm back here. And I can step through this again. I also, because I know the first bunch of statements worked, I could choose to just set a breakpoint. So I can set a breakpoint there by clicking on it. And if I hit continue, I'll run until I hit that breakpoint. Before I do that, let's go back and look. The program counter is back at 0. Notice that the other registers haven't been reset. Okay, they're still what they were before. So we changed T0 to 2. We changed T1 to 9. They're still like that. If I don't like that, if I go, I want to kind of see them change again, I can just click on them and change them back. So I can change all these back to 0. In this case, it doesn't matter. It would have worked if I just left them. But if I want to have a little more confidence that everything's getting redone, I can set them back. And I'm going to hit continue. So that just jump down to, I won't jump, I execute the program until I get to this point. And now I'm going to step over this one again. Okay, now I need to go way down to T3. Okay, so T3 is a whole bunch of Fs. I don't know if you can, hopefully you can read that at the back, but it's a whole bunch of Fs and a 9. Is that right? So I see people nodding. So yeah, that is negative 7. So 2's complement, 32-bit, negative 7. If I don't like looking at that hexadecimal, let's see, where is this? There it is. I can change it to decimal signed and go look for this again, and it's negative 7. It's easier to read. Something else I could do is I could say interpret it as decimal unsigned, in which case it's almost 4 billion. So, but I don't want to interpret this as decimal unsigned. Okay, so it's the same bits. I can interpret it. I want to interpret it as a signed number, and in this case, it's correct. Okay, now I can just, let me move this back down here. Okay, so my program counter is here at 16. This is in hexadecimal. No, I changed it to decimal, actually. So, yeah, so that's a decimal 16, which matches what I told you on the board. So it hopefully shows you this I loop. There's nothing magic about it. It was just a label that was given the address of this instruction. And if I click step, you'll see the program counter doesn't change. And I stay on this yellow line. This is just an infinite loop. It's just jumping back to the same instruction over and over again. I can hit continue. It'll stay there for a really long time. And if I want to stop, I can hit this stop button. So let me show you one more thing here. Let me go back to settings here. Okay, so show us in hexadecimal again. Let's look at this. You can actually see like there's stuff in memory after my program. This is why I wouldn't want to keep going. If I kept going, I would just interpret all these other values as instructions and my computer would be doing crazy things. So this first opcode, load immediate T02, okay, so somebody remember this number. So 002-00293. If I go back here and I just say, let's not put in 2, let's put in 3, and let's compile and load, that first instruction, the opcode just changed. Okay, it went from 002-00293 to 003-00293. And the reason is I changed the constant from a 2 to a 3. That constant's embedded right in the instruction. So if I went and I changed other things, like which register is this, another number will change inside of here. If I change what instruction it is, another number will change. If I do, let me go back here and do one other thing. If I put a different instruction in here, let's just do load I T110. Okay, so I just put another instruction in, compile and load. Now you'll see that my infinite loop at the end moved down 4 bytes in memory. Okay, so it's a hexadecimal 14 or decimal 20. So if I had actually used the number, hex 10 here, I would now actually have to go update my program. This is why we want to use symbols, because the assembler did it for me automatically, right? I loop moved to address 20 or hexadecimal 14, and that automatically got updated by the assembler because I used a symbol. Does that make sense? I think that's, I think I cannot go to the next. Actually, one other thing I can tell you about. So just looking forward, basically the I/O devices are also emulated. So for the first couple labs anyway, you're going to use this editor, the disassembly and single stepping it, and you're going to watch these registers. Okay, that's enough for you to make things work. But basically, this emulator actually emulates your switches and your LEDs and all sorts of other things as well. So you can actually even see what would be happening on the I/O devices in the emulator, which is going to let you debug even more of your labs. Yeah. Does it? Can you say it louder? It does show you a waveform for speakers. That's the one where it's actually kind of the weakest, because it doesn't give you like a sound output. So good question. And yeah, make sure I posted the rubric for Lab 1. So you'll see half the marks are for how prepared you are when you come in. You should know CPU later. You should have a program written. Maybe it's not fully working, but you should understand what you've written and have taken a good attempt at it. And the TA is going to check that you actually know how to run CPU later and you understand the instructions in your program. And then by the end of the lab, you're going to demonstrate a fully working program running in hardware where you can actually step through it with GDB. So all of this stuff is in the tutorials for the lab. And we're pushing you to make sure you follow those tutorials for your own good. So you really learn these tools.